I'm still Francois Rene Rideau, and today I'm going to give my most LambdaConf talk ever. It is about Merkle proofing, or how functional programming meets algebra, differential calculus, metaprogramming, and OO, or how math can automate your programs. And happily, it's much less rehearsed than the previous talk, so bear with me and thank you for being with me. Okay. The prelude is that this talk is about the path and not the destination. But let's discuss what the destination is. My thesis is that you can use this magic thing called zippers, and that can make your programs faster, simpler, and give you this thing called Merkleization for free. And I will go so far as say that every data structure, when you define it, should come automatically with zippers. And that today it may look like advanced math, and tomorrow it will be table stakes for all your programming languages. And my wider thesis is that there is a synergy between functional programming, algebra, calculus, metaprogramming, and OO. It all works together. So what is Merkleization? Who here knows what Merkleization is? One. OK, who does not know what Merkleization is? Most people. OK, that's fine. Merkleization is just this idea that if you have a one-way hash function, say SHA-256 or whatever, if you have that, then you can assume, and there are enough bits, you can assume that there are never going to be any collision in your lifetime or in the lifetime of the universe. And therefore, you can use it as a pointer for a content address store. If all you have is a DAG, a directed acyclic graph of data, each node can be assigned, can be translated to bytes. You compute the hash of those bytes, and by hypothesis, the only bytes ever used in your system with that hash will be those bytes, and therefore that hash is a valid pointer to your data in the content address storage. This is the trick used by Git. Anyone here has heard of Git or used Git? Anyone here has not heard of Git or not used Git? OK, better. So Git uses it. Any kind of content address storage systems use it. Deduplication is based on it. If you use a storage system that automatically saves on duplicates, oh, they have the same hash, they have the same thing, let's store it only once. If you use peer-to-peer networks, things like Nutella, etc., use this trick. If you try to timestamp, have a timestamp server that says, hey, I have seen this data at this time, it uses this trick. If you use blockchain such as Ethereum or whatever, it uses this trick. And there is the next step in Merkleization is the notion of Merkle proof. You can certify that some data structure has been, you can commit to the top of your data structure, here's the hash of everything. Because of the one-way hash at every step, it actually commits to the entire data. It points to the entire tree of data. And then you can exhibit only the parts you want. And in a logarithmic size, you can prove that this bit here is actually a leaf of that big tree. OK. So let's try to exhibit that with a diagram. I'm sorry, I never learned how to use diagrams. So let's do it the hard way. Where's my? OK, let's imagine you have a tree, a binary tree to simplify like this. And you want to show that this element is part of that tree. So you will compute the hash for this element. And then you can compute it from the hash of these leaves. And you can, by recursion, like as a synthesized attribute, compute the hash of everything. And there you go. So how do I, well, you can write ad hoc code to do that. Ad hoc code is, you can always write ad hoc code to do everything. But can I simplify that computation or make it part of something systematic that can be automated for me instead of having, every time I have a new data structure, I have to write a completely new set of code to explain how I can have Merkle proof of that. And if my data structure is very complicated, then I have very complicated code. Of course, there will be a bug in it. How can we help that? Sorry. Is this diagram, is it clear enough what I mean by having a first Merkleizing? So I will compute the hash of each node, and we synthesize the hash of the whole thing. Is that clear? And if the same node is reached twice, that's OK. That's allowed. It's what a directed acyclic graph. There are just no cycles. It's all directed here. OK. So is that clear so far? Computing a Merkleization? OK. Let's go. Can we then make it easier? So there is a magic trick called the zipper, invented by Gérard Huet in 1997, that is a data structure that corresponds to a pointed subtree in a tree, which is what we have here. We have a big tree here. We have a subtree here. And we have a notion of the tree and the subtree. So what we really mean here is that we want to have a data structure that is made of erasing this node and having, that here, we have this and that. So we cut this link here, and we want to have a data structure which is the thing above and the thing below. So we want to cut a link and have that. So how do we represent efficiently in a pure functional language that thing? Well, first, the subtree is just a subtree, so that's easy. And then you want to represent the path that leads to this subtree. Well, this path is made of what? It's made of basically that thing here, which is a tree to the left and the data that you're to the right. And then there's this thing here, which is the data of that string to the right and the data that you are to the left. And you have this thing here, which is basically the data that you were to the right and the subtree that was to the left. So what do you need to know? You need to know at every step left or right, and the tree on the other side. And that gives you a path. So I start here. Well, to reconstitute the upper tree, I need to make sure that I was to the right and I have the tree to the left. And here, can I have a pointer? I don't know. The pointer is too small. OK, so I'm starting here, and I reconstitute that node by adding that thing to the left. Then I reconstitute that node by adding the thing to the right. Then I add that node by adding the thing to the left. So basically, it's a list. So I have what's a binary tree? A binary tree is, in algebraic, it's t equals 1 plus t2. It's either a leaf or a pair of trees. And my zipper will be, or my zipper, whether my zipper path or zipper context, will be a list of 2 times t, which is left or right at the 2, and the t is the thing on the other side. So it's a cool trick. Ziverge explains it. And what do we do then when we want to, when I want to show a path from the subtree to the big tree? I can just give you the zipper. The zipper or the zipper path gives you the path from the subtree to the big tree, and your zipper is just a pair of the subtree and the path. That's what they call the zipper. And so you can, the zipper is just a point, the data structure plus a point inside it. And you can zip it up to get the data structure on top, and you can zip it down to go back to your subnode. So that's why it's called a zipper. You can zip it all up or zip it all down. OK. So it was a cool hack published by Gérard Huet in 1997. Then Conor McBride systematized it in a paper in 2001 that says the differential of a type is the type of its one-hole context. Very nice paper. And actually, there's a deeper theory of that. There's something called combinatorial species, like published by Category Theorists, that kind of talk about that in 1981. And then there's Jorge, forget his first name, who published a thesis on this kind of thing in 2010. And of course, in the future, it will be a basic feature in all your programming languages. So let's, to generalize it, let's go back to algebra. So what are finite data types? It's easy. You start from the empty type. You can add a new element to a type. You can add one. And so everything that can be generated from 0, and you can add one thing at a time, is a finite data type. And then you can define operations on it. So you have 0, you have 1, which is 0 plus 1. You can have plus addition, like it's a disjoint union of two types. And you can have the Cartesian product of two finite types. And this has the structure of a summaring. And actually, it's isomorphic to the set of natural integers. A finite type is up to isomorphism. It's just the same as any other finite type with the same number of elements from a mathematical point of view. Of course, in practice, you will want to remember which isomorphism you are using. Otherwise, you're forgetting all the information. But if you step back and you don't leave that as an exercise to the reader, it's just the same as n, the set of integers. We can give a meaning to z, q, r, and c in this context, and I leave that as an exercise to the reader. I can just tell you that, for instance, minus 2/7 is a data type that means except on weekends. Okay, you can extrapolate from that. Okay, but of course, finite data types are fine, but you want to go further. So the first thing you add is variables, type variables, A, B, C. And once you have those type variables and plus and multiplication, you have what we call polynomials. And you can have polynomials of one or multiple variables. And what becomes interesting is that your variables do not have to quantify only over finite data types. You can invent bigger types, infinite types, and now your variable can also quantify over those infinite types. Of course, when you start talking about infinite types, if you still say that everything is up to isomorphism where any bijection in the set theoretic sense is fine as an isomorphism, then it just all the infinite types or equivalent or just equivalent to all types with the same cardinal. This is not very interesting. In practice, you will want to restrict much what you call as a morphism, or what you call the equivalent between types. This is out of the scope of this talk, but just consider that when you say, is a list equivalent to another to a list? Yes. Is it equivalent to a tree? Usually, no. Like you want to have some notion of the two are different. Okay. You can also try to define exponentials, so functions from b to a or to a from b is the same thing as the exponential a to the b's power. And that's also something that I will consider out of the scope of this talk. You can do that. It's cool, but it makes things more complex and not interesting right now. So what are the simplest infinite data types we can have? I would say it's pure inductive data types. So that when you define a type in OCaml or something like that, it's what you have. You define a type in terms of here are the constructors, and we'll find the least fixed point of these constructors. And to a first approximation, your constructor defines a polynomial. The least fixed point will be called mu of p, where mu is the least fixed point operator and p is polynomial. And the basic thing is that mu of p is invariant by p. P of mu of p is the same as mu of p. It's a smaller, and it's not just that, it's the smallest fixed point. So we'll go there, look at a bit, but the simplest example is a list. A list of A. What is a list of A? It's either 1, that is a null, a terminator, or, so that's the plus, it's a disjoint sum of, or a pair of an A and a list of A. But this is a circular definition. How do we remove the circularity and transform it into a least fixed point operator? Well, you say, here's my polynomial P of A. It's a polynomial that to x associates 1 plus A times x. And then you say, well, a list of A is a least fixed point of this polynomial P of A. So that's how internally your compiler might do it. And insert diagram. I don't know if I can do a new page. Do I need to explain what a list is? Or this is a functional programming conference. Everyone knows what this is. Okay. Similarly, for binary tree with A at every leaf and B at every node is just either you're a leaf, then you have an A, or you're a node, and then you have a B, and then another binary tree of AB, and another binary tree of AB. So this is how you define it as in a recursive way, the recursive definition, how you might define it in OCaml, for instance. And if you want to remove the circularity and replace it by least fixed point, you define a polynomial Q of A and B that to type X associates A plus B times X times X. And then you say the binary tree is just the fixed point of that. I hope I haven't lost you yet. It's pretty common for functional developers. So the main thing about algebra is that algebra helps you to think in terms of structures. Like elements, you can always encode things differently. You can, so elements don't matter. What is a number? A number is anything. What is interesting is what is a structure of numbers? What is a field of a ring, a semi-ring, or whatever of numbers? What are the underlying structures? And thinking in terms of structures rather than isolated elements is what modern mathematics is all about. And the people who think about it the most are the category theorists these days. But basically, you want to think in terms of those. A number doesn't exist. The set of finite numbers exists, or the set of relative numbers, the set of inductive types exists. And an index of this type in isolation does not mean anything. OK, so now we can introduce differential calculus for data structures. So who here has ever differentiated a polynomial? Who has not differentiated a polynomial? OK, well, let's do. OK, so differentiation is. OK, well, for data types, now we have polynomials. So P of x, where x is a data type, will be a sum of product or choice between records. That is, I will have different terms, just like I define my recursive data types. A list is a constructor, nil, or a constructor of two things. So every case defines one of the terms of the sum, one of the terms, whatever. And every term is a product, is a record. Okay, so we have and now I will define dy divided by dx as a type of wholes of type x in y. So if we go back to this thing, I will have a type of trees or whatever, and so it goes here. And I have a type of trees, but I want to have a type of holes. And the holes are indicated either by one single arrow for one hole, or some people notate it as a big circle, or whatever. But I want to be able to say that, well, I'm going to remove one element from this data structure. And if I try to express it in terms of polynomials, I will get just the right thing. So if I have a polynomial which is a sum of terms of that took an times x to the n, that is, each choice has the recursive term appear n times, and then I have also data associated to that node that doesn't depend on x. When I differentiate it, I get the sum of n x minus x to the n minus 1. That is, let's see, if a given node I have something and I have 4 choices here, well, the path may be here, or it may be here, or it may be here, or it may be here. So I have 4 different possibilities. And then I will have still to show the constant that is here of type A. And I have x now, the remaining. So if I pick this one, well, there are 3 that remain. So 4ax to the 3. And in general, to reconstitute the bigger thing, if you have n choices, if you are a product of xn times, well, if I pick one, then there's x appears n minus 1 times, And then I still have the things, the factors that correspond to the node. So I will need to have n, which tells you the position. The constant term needs to be there. And then I have the variable that appears one fewer times. And when you do calculus for continuous functions, that's how you compute like the minimum or the maximal of a polynomial, things like the zeros. You can do lots of things in calculus for numbers, but you have magically exactly the same structures that happens for data structures, and the same polynomials have the same derivative, and it means something useful. And in this case, it means, what do I need to know to reconstitute the bigger term from the smaller term? So what is the one whole context that gives me the bigger term from the smaller term? So p prime of x, the derivative of p, tells me, well, if I have an x, how do I get the bigger term? And of course, if you want to, the terms a0 does not appear here. So here's a sum from n from 0 to infinity, or however many terms you have here. The term from 1 to how many terms you have, because the constant term where x does not appear with x with n equals 0, well, x does not appear from it, so you can't build a bigger term from your x if x does not appear in the constant term. So the constant, well, there is one case that doesn't appear in the derivative. The constant term from the p of x does not appear in the derivatives. It becomes 0. Okay. So what happens now? I have an inductive data type. So if I have, let's introduce a new page. Let's go here. So if I have an inductive data type, so I have, so first I may be n level deep. At every level, I will need p prime of and we'll need a term p prime of t to tell you what happened from this level to this level. And there also a p prime of t, and there also a p prime of t. So in the end, I will have a list of p prime of t will correspond to my path from the inner t to the outer t. So if I have an arbitrary tree defined by an arbitrary polynomial, an arbitrary data, recursive data structures with one variable to simplify to go from one to the other, at every step I need to at every step I have a p prime. Every step of the node is defined by polynomial p, and therefore the thing without a hole is a p prime. And since I have n level of steps, I have a list of p primes. So if you want that more formally, for those who like math, you define mu of p, the list fixed point, as the minimal of the fixed point which verify p of f equals f, and that you can have a big mu of, you can define something big mu of p, and big mu of p would be the limit of the p to the n. Basically, you look at all the trees of depth up to n, and since your depth is finite, there is some n for which that is the case. So, and of course you need to, since it's depth up to n, there are lots of terms that is up to 2, which are included in up to 3, so you need to identify them, and then you can have the limit when n becomes arbitrarily large, and this gives you the limit of applying p an arbitrary number of times to t. And then if you have this operator applying p an arbitrary number of times to t, then you apply it to the term 0, and that will give you magically the least fixed point. And now my path will be just the derivative, this magic formula, and that gives you the list of p prime of t, which means that you can now take any, and you can generalize also to multiple variables, but you can take now your data type definitions and automatically generate the zipper that comes with it without having to do it manually. You could do it manually, and that's what I do when I don't have better tools. And it is very automatic process, or you can do it automatically. So zipper, what is, let's take a type T, which is defined as a fixed point of a polynomial. So you have a recursive data type. And so it can be expressed like this. And I define the zipper path as this list of p prime of t. And then my zipper is a t times this path. And that gives me basically how to get, for any arbitrary type, reconstituting a bigger element of the type from a smaller one. So you can, it's kind of the opposite of a lens. The lens takes you, here's a process for going from a bigger element to an interior element. This is a lens with negative focal distance, that where you take a smaller element and it will complete it into a bigger element. And not just as a function, so lenses usually are presented as functions. All you can do is apply them. Here it's as data, so it gives you each element of the path, which means that you can do funky things such as remove just one or add two, which you can't do with a function. With just a function, you can either apply the whole thing or not apply the whole thing. It comes as a one all or nothing package. With a zipper, you can go up 1 bit or 2 bits or 3 bits. You can go back down, and it's reified as data rather than embodied as a function. OK, so what can I do with the zippers? First, I can do things much faster when I'm only modifying the things that are under focus. So you have a big tree, and I want to do lots of work on one element under focus. If I start from the root every time, I will need for every operation to go down n levels. So if my tree is balanced, it's a log n of operation. If I keep my data as a zipper, and I do 1,000 operations on the thing under focus, now I don't need to multiply all my accesses by a log n factor. It becomes O of log 1. So yay, O of 1 focus access instead of O of log n focus access. Yay, faster. Also, if I'm not going exactly at the same place, but I'm going to do sequential access, I want to add an element here, then add an element here, or add or modify an element here, etc., etc. At every step, I will have to not go all the way up, but go only 1 bit or 2 bits. And if my tree is balanced in any way, at every step, the probability that I go up n times decreases exponentially with n, which means that my for sequential access is still in amortized O of 1. So I have, certainly I must do one thing once. Every other time I must go twice. Every quarter of time I must go 4 times. Every 8th time I must go 1/8 time. So have 1 plus 1/2 plus 1/4 plus 1/8, etc. The sum is 2. So basically the amortized cost of doing sequential access is just add a factor 2. So it's still O of 1. Yay. So amortized sequential access is cheap. And now, is there any locality in your data? So if you access data at random, you don't gain anything by using zippers. But if there is any locality to your data, oh, there are a bunch of things done in sequence, and then another done in sequence, and I cannot predict necessarily statically in advance where the locality is, but just by using zippers, I will dynamically detect that local access, and pay O of 1 instead of O of log n. So I will accelerate any data pattern of data access that has locality. So everything faster and dynamically discovered. You don't even have, whoever implements the data structure doesn't have to know which parts of the program have locality. By using zippers, everything goes faster. Everything is simpler by using zippers this way to implement Patricia Merkle tries. I got my thing in 10 times less code than Ethereum did in its Go implementation of Patricia-Merkle tries in Go. Well, some of it is I was using scheme and then Haskell instead of Go, so maybe if you program it in Go, it would not be 10 times, it would be only 2 times better. And also I had 2 times the features. Now I have incremental access very easily, have sequential access very easily, I have a binary method easily, have Merkleization very easily, all kind of things that you needed to do by hand if you didn't use zippers. And I also don't have to write the code twice. I found that if I don't use zippers, a lot of operations I need to write once when I do everything at once, and I need to do it a second time if I want to do incrementally. And it's a bore, but if I use zippers, I can write it once in the incremental case, and the total case can just be deduced trivially from that. To the point that sometimes I wonder if I should not use zippers as my primary data structures in all my algorithms. And just at the end, if you really want the node, you can just zip up and get your whole tree at the end. But actually, most of the time, you can just work with zippers all along, and everything goes faster and simpler. Oh, I can get my Merkleization in 2 lines of code. So let's suppose that I have, and this is generic for any data structure, of course. This is not 2 lines of code per data structure. This is 2 lines of code for all data structures. So for any data structure T that is defined or not defined as mu of P, I define the zip path. So if it's not recursive, it's just P prime. And if it is recursive, it's a list of P prime of T. And then my proofs are just a list of P prime of H, where H is a data structure of my hashes. Basically, you replace every tree along the path, every node along, every tree on the side along the path, you replace it by its hash. I'm replacing that by its hash, this by its hash, this by its hash. So instead of having a list of 2 times T, I have a list of 2 times H, where H is my hash. And then this is my Merkle proof. And this algorithm here in 2 lines of code is valid for all data structures, not just for one, in 2 lines of code. So before that, every time you had a data structure, you had to do the hard way without knowing the theory of derivatives, encode the ad hoc thing that would get you your Merkle proof. Now you can have Merkle proof for free if only you use zippers in a uniform way. So what does it do? Let's see. I'm using a monad because sometimes my node access is a monad. So first I'm transforming my tree in a zipper. Then I'm refocusing it on the node that I'm interested in. And then I throw away the data for the node. I'm focusing on the path back to the top. I replace every tree on the side by its hash, and I return the thing. Ta-da! I got my Merkleization for free. This is composable. So if I have a data structure defined in terms of nested data structures, etc., I can easily compose those Merkle proofs. It can be seen as part of the general theory of optics, if you know about lenses and things like that, except that, once again, it's optics that is not just data functions that you can either apply or not, but it's data that you can also deconstruct and reconstruct bit by bit. You can go one level up and 1 level down, whereas with the lens, you can just apply the whole lens or not apply it. And it can dynamically simplify your algorithm and detect the patterns of sequentiality and locality. And you can also do, say, permission checks at every level of access. Do you have access to this level or not? Because you have a list of branches or things you're doing. You can do a lot of things because it's verified that you couldn't do with lenses that are opaque functions. Very quick. So doing zippers by hand is error prone. If I give you an arbitrary data type and you have to manually write the derivative, it's hard. You will make mistakes. And if you change one data type at some point by maintenance, now you have to change all the derivatives and all the derivatives or whatever you have. So it's a maintenance nightmare. if you have to maintain those derivatives by hand. Unless your code is perfectly designed, you never need to refactor it. That happens sometimes, not all the time, but sometimes. But in general, it becomes a maintenance nightmare if every time you define a data structure and you make a small change to it, you have to redefine the zippers and plug them at the right place everywhere. And you could define your type, some kind of type parameters that you will magically plug with the right derivative at the right time by hand. That's possible, but that's hard. And if furthermore you use object orientation or type classes or something like that to define and refine your data types incrementally, then you find that the derivative is a global property of your data type, not a local property. So you can't, you have to, at the moment you instantiate your class, then you need to instantiate the right derivative for that fixed point. Doing it by hand, it can work, but it's very error prone. And my friend Olin Ziverge has this motto: I object to doing things that computers can do. So what we want is have automatic differentiation. It's a topic that is very familiar now because people use it all the time in AI because they automatically differentiate computations to do backward propagation of they compute dynamic fixed points of numerical values for the neuron, for their neural networks. Well, instead of doing that for numerical values for neural networks, we can do that for type definitions. And all we need is type-directed metaprogramming. And if you have, in a dynamic language, such as Scheme, that I've been using, you have first-class type descriptors on them. So you have an explicit data representation of your polynomials, and you can extract you can compute your derivatives this way. That works great in a dynamically typed programming language. If you want to do that in Haskell, I haven't done it yet. I think it's possible with template Haskell and things like that. It will be a bit to do in Haskell. Maybe some of you can do it. And of course, in the future, where you want all your programming languages to just give you that by default, you could add in your programming language, in the compiler, a special thing just for differentiation of types as a primitive, or you could have some more general purpose metaprogramming in which you can write and extend your differentiation of types. It hasn't been done yet, but the time has come to do it, and you can do it. It's definitely possible. So my conclusion is, of course, that zippers can be used for speed, simplicity, or Merkleization. Every data structure in the future will come, or should come, with automatically computed zippers. Like computing zippers should be a primitive that your language provides to you, either as a built-in or as a macro that you can define yourself, if possible. Today, it may look like advanced math, but actually, tomorrow it will be table stakes. Like, of course, you will have, just like for the purpose of neural networks now, AD of formulas become table stakes. In the future, automatic differentiation of data types will become table stakes. And we see that there is this synergy between functional programming, algebra, calculus, metaprogramming, OO. It all goes together. Like lots of people try to think, oh, I like FP but not OO, or yeah, I like programming but not math, or I like math but not programming, or I like programming and not metaprogramming. Why? It all works so well together. It's like you should not have to be afraid of all those things. You can just use them as a user or implement them as a more advanced user. Enjoy. It's not, these things are not opposite to each other. And maybe that's why this is my most LambdaConf talk. Most of my talks have been on the margin of functional programming, like things that are like orthogonal persistence, reflection, how to tell better stories to have better languages, evolutionism, blockchain, decentralized applications, first-class implementations, prototype, object orientation, orthogonal persistence again today. And this talk is about math. Math is practical. I think that's the essence of LambdaConf. We're not just people who understand things and they, oh yes, the theory, but we don't care about the practice. We're not just people who build things that we don't care about the theory. We are people who do things because we understand them, and we understand them so that we make them happen. And that's what I love about LambdaConf. It's about the can-do, yes. We like understanding because it helps us do things, and we like do things because it's part of this higher marveling at the universe. So I love this quote: the hacker, someone who figured things out and made something cool happen. This is what LambdaConf is about. So I'm proud to end my LambdaConf interventions with this most LambdaConf possible talk. Math is practical. I'm actually using this kind of technology in my data availability network called skyprotocol.org. We'll have to change the name because other blockchain projects have adopted the name too. Doesn't matter. There is a semi-formal description of zippers and tries at the following URL. I have a Twitter X account. I have a blog. Please contact me for whatever reason. Thank you for coming for this talk. I'm sorry it was not as prepared as it could have been, but that's why there are questions and answers right now. Thank you.
Before we get to the Q&A, I just wanted to let everybody know if you could raise your hand first, then I can come around to the microphone, and the questions will then be recorded as part of the presentation.
Yeah, hi, great talk. Do you know, so zippers looks like an editor with one hole, so like we can...
Yes, you add a hole to your data structure.
Yeah.
You take your data structure, you cut it. You cut one hole in your data structure.
Yeah, do you know how works or articles about, is it possible to have like two holes or many holes? And
yes, you can have two holes. You can differentiate twice. You can differentiate n times. You can do all kinds of funky things, yes. And you can generate to multiple variables. You can realize to what happened in the presence of exponentials. And then you have logarithms too, and logarithms are weird for data types. Yeah, you can have lots of fun with that. But even if you restrict it to just polynomials, you already have lots of power. So you can go arbitrarily complex or just very simple. In every case, it can help you.
Could you talk a bit more on the relationship between zippers and optics? I've never heard of that before, but sounds interesting.
In an optic, you start from an arbitrary point, and you have a path that says, from that point, I will go down this way to extract a smaller object. And with a zipper, you start from an object, and you will reconstitute a larger object from it. That's why, in a way, a lens is something that takes an object and extracts data from it. And a zipper is something that takes some object and reconstitutes something bigger from it. And if you have a pair of extracting data and then building something from it, you can call it, I don't know, generalized zipper. I don't know. It's probably a name somewhere that I don't know. So let's call it a zipper lens. And you combine two zipper lenses, you have still a zipper lens. That is, in the end, you still have extracted data and then build something from it. Even if in the simplest case, what you extract from the data is unit, that is no information from it, and you just build something. But you can, two zipper lenses compose, or it's still a zipper lens. So, yeah. Except that, again, most presentations of lenses in Haskell, for instance, is just a function, a whole or nothing function, where a zipper is data. So you can decide to go just one step or two steps or three steps up your zipper. You can do that with a lens. Or you could invent lenses as data, actually. You could have this is a reified lens. I think that John DeGauss calls them reflective lenses and reflective optics. So yes, and that's super useful. That is, yes, optics need not be just opaque functions. It can be open data. And then you have better error messages. You can have efficient cancellations of things that cancel each other. You can have lots of good things from optics as reflect or whatever, reified data, reflective, however you call that, as data rather than functions. Everything is clear. Well, I'm glad that I was that clear.
Hi. I'm not as familiar with the literature, but the 97 paper you were referring to, I noticed when you were talking on the DAG, and then you were using the term tree loosely.
So in this 97 paper, it was just for binary trees, but it can be, in the 201 paper, it's generalized for any kind of tree or data structure defined as a polynomial.
It expands to DAGs as well.
Yeah, it's DAGs. Yeah, yes. It's DAGs, really.
Yeah, because I haven't read these sort of papers, so I don't know if they use a different definition of tree than I learned it, but or you're just using the term loosely.
You can share the node. If the same node appears twice, it can be shared. It doesn't need to. You don't need to copy.
Oh, I see what you're saying. You just duplicate it. So you
duplicate the reference. You don't need to duplicate the whole thing. It's not O of n. It's O of 1 when you share reference.
I see. I think I see. So if you duplicate it, then it forms a tree that can then be mapped to a DAG.
Yes. When you walk it, it's like a tree, but the memory representation is more like a graph, and you can maybe you have a comparison operator to see if two things are equal and do optimizations based on it. But yes.
Okay. Thank you.
All right, one more. I think this is a pretty simple question. When you're like working with optics, you have your base data structure and then your derived optics normally, right? You mentioned working like zipper first, like you define the zipper first, and then presumably you'd have to have the base data structure that you can zip it back up into, correct?
So you need to define your base data structure first, and then you automatically compute the zipper from it. And then you find that often it's simpler to use your zipper instead of your data structures in all your inside functions, because your inside function will spend their time focusing and refocusing, and instead of always go O of log n, you can just stay with the zipper and go up only as much as you need to and go down. So things become more efficient if internally you use the zippers everywhere. Do you want to expose the zippers to your API? Maybe, maybe not, I'm not sure. A trivial zipper, a zipped up zipper is trivial. It's just the point and an empty list of p prime, so it's pretty trivial. And then you can do optimization such as, you always have a list of t's and then an optimized data structure. There are lots of optimizations you can do up to isomorphism, lots of cool stuff, a lot of cool data structure transformations you can do to be efficient. But the principle is the same. Like you can automatically derive your zipper, and if you have optimizations, you could also automatically generate your optimizations. For instance, a list of units can be reduced to a number. Yay! I can, instead of having n pointers, I just have a number of size log of n. There are plenty of optimizations you can do. Or a number that you know is bounded. Now you can represent it in the bounded integers, qubits. And this can all be done automatically. And when you do it automatically, it's up to isomorphism, but you have to remember which isomorphism you are using. So yeah, but that's part of the difference between computing and mathematics. In mathematics, you throw away the isomorphism. In computing, and you keep it tightly.
All right, I think that's about it. Let's give another round of applause for our presenter.
Thank you.